We use a systematic method called rice table method if we have initial concentration of some species and sometimes a combination of initial concentration and the equilibrium concentration of some species. We can use that information to find the equilibrium concentration and K value for a reaction. And we will discuss that systematic method in this video with multiple examples. So keep these points in mind when we solve that rice table method. So first we have to write a balanced chemical equation and then set up the equilibrium expression just like we are doing K equal products over reactant. Instead of writing the or plugging in the given numbers, just write that expression first and then we have to substitute the numbers and set up the chart, and that initial concentration, if it is given, we will find the Q. If it is the equilibrium concentration is given, we will find the K value. And the unknown, we will put X and we will substitute and we will find the, or we will solve for finding the value of X. So let us see some examples and then we can go through each step. Question is, at 700 Kelvin, carbon monoxide reacts with water to form carbon dioxide and hydrogen, and the equation is given: carbon monoxide plus H2O gives CO2 plus H2. The equilibrium constant for this reaction is also given, which is 5.1, and consider an experiment in which 1 mole of carbon monoxide and 1 mole of water. So it is 1 mole and mixed together in a 1 liter flask. So we have moles and volume so that we can calculate molarity at 700 Kelvin. Calculate the concentration of all species at equilibrium. So what we have to do, first we have to write the reaction and make sure it is balanced. So in this case it is balanced equation, and then we have to write the initial concentration. Like I said, 1 mole divided by 1 liter will give us 1 molar concentration. So carbon monoxide is 1 molar and water is also 1 molar. And in the beginning, we do not have the product. Carbon dioxide and hydrogen will be 0. And then third step is we have to write the change. So since the coefficient of carbon monoxide is 1, we can just write negative because the concentration is going to be decreasing for the reactant and we don't know how much is that, so we will just represent that one by putting X. Same way for water also, the coefficient is 1, so I can just put negative X. That means it is only 1, so that is why I don't put any number in front of X. So since it is 1, just negative X. Same way for carbon dioxide, it is a product, so I will put plus, and coefficient is 1, so only 1X. And for hydrogen, again it is the product, so plus 1x, or simply we can write x. And the fourth step is to write equilibrium concentration. So what is going to be at equilibrium is we are just adding these two steps, that is the initial concentration plus change. That means 1 minus x. And for water also 1 minus x. And for carbon dioxide it will be 0 plus x, that is just x. And for hydrogen also 0 plus x, it will be just x. So now we have the equilibrium concentration in terms of x. So what we have to do is we have to calculate the K value, which is concentration of products divided by concentration of reactants. So that equals concentration of carbon dioxide and concentration of hydrogen divided by concentration of carbon monoxide times concentration of water. So that equal, we have in terms of X at equilibrium. So carbon dioxide is X and hydrogen is also X. So I can put X square divided by, for carbon monoxide it is 1 minus X, and for water vapor also it is 1 minus X. So it is 1 minus X times 1 minus X, that I can write it as 1 minus X to the power 2. And the K value is given as 5.1. So since it is a perfect square, what I will do is I'm going to take square root on both sides. So 5.1 equal square root of 5.1 equal square root of x square divided by 1 minus x to the power 2. So that means square root of 5.1 equal x divided by 1 minus x. And that means I can simplify that. Square root of 5.1 is 2.258. That equals x divided by 1 minus x. And now to isolate that x and to take off that 1 minus x from the denominator, I will multiply on both sides by 1 minus x. So I will get 1 minus x and 1 minus x will get cancelled, and I will get 1 minus x times 2.258 equal x. So now I can expand. So that means 2.258 minus, and then I can multiply that one with x, 2.258x, that equal x. And now let us take the x on one side, x terms on one side. So that will be 2.258 equal 2.258x. So the negative 2.258 from the left side will change to positive on the right side, and we already have an x on that side. So that equal, so this is 1x and this is 2.258x. So when you add, you will get 3.258x. And now, so what is x? X equal 2.258 divided by 3.258. That equals 0.69 molar. So x is 0.69 molar means I have x on the right side of the equation, that is concentration of carbon dioxide, and that equal concentration of hydrogen, both are x, so that equals 0.69 molar. And on the left side we can say that concentration of carbon monoxide will equal concentration of water because both are 1 minus x. So that equal 1 minus 0.69, that equals 0.31 molar. So that's the answer for the equilibrium concentration for all species in this equation. Alright, yes, second question. At a certain temperature, 1 liter flask initially contains 0.298 moles of PCl3 and 8.7 times 10 to the power negative 3 moles of PCl5. After the system had reached equilibrium, 2 times 10 to the power negative 3 moles of chlorine was found in the flask. Gases PCl5 decomposes according to the reaction. PCl5 gives PCl3 plus Cl2. Calculate the equilibrium concentration of all species and value of K. So what we have to do first step is we have to write the reaction. So we just copy the reaction given. PCl5, that is gaseous phase, gives PCl3 gaseous phase plus chlorine gaseous phase. And then we have to write the initial concentration given. It is given as 1 liter flask and the moles given. So what we will do, moles divided by volume, that will be our concentration. So since the volume is 1 liter, I can take the same number as moles given here for the molarity. So for PCl5 it is given, and for PCl3 also it is given as initial concentration because initially contained. And then we have 2 times 10 to the power negative 3 moles of chlorine found in the flask at equilibrium. So that number will go at equilibrium, that is 2 times 10 to the power negative 3 for chlorine. And now I will write the change. So all coefficients are 1. So I can write for the reactant negative x, and for PCl3 plus x, and for chlorine also plus x. And now at equilibrium concentration, what will happen? We have to add step 2 and step 3, that is 8.7 times 10 to the power negative 3 minus x. And for the product side, it will be 0.298 plus x. and for chlorine it is X, which is already given. And now our next step is to find the X for X value is already given. So just substitute that X for PCl5 and PCl3. So for PCl5, I can write PCl5 concentration equal 8.7 times 10 to the power negative 3 minus 2 times 10 to the power negative 3. So what I have to do in that case is I can take that 10 to the power negative 3 out. So 8.7 minus 2 times 10 to the power negative 3, that will be 6.7, right? 6.7 times 10 to the power negative 3. And now for concentration of PCl3 equal 0.298 plus 2 times 10 to the power negative 3, that will equal 0.300. And for chlorine it is already given, which equal 2 times 10 to the power negative 3. So we got the concentration, equilibrium concentration. So for we can write here for PCl5 it is 6.7 times 10 to the power negative 3, and for PCl3 we got 0.300, and for chlorine it is already given. So we will write like that, and we can calculate the K value now. So K equal concentration of product divided by concentration of reactant. So that is PCl3 times Cl2 concentration divided by PCl5 concentration. That equals, substitute the numbers, 0.3 times 2 times 10 to the power negative 3 divided by 6.7 times 10 to the power negative 3, that equal 0.3 times 2 divided by 6.7, because 10 to the power negative 3 and 10 to the power negative 3 we can cancel. That equals 0.6 divided by 6.7. We will get 0.0895. When you move the decimal, we can write 8.95 times 10 to the power negative 2. Let's see another question. Carbon monoxide reacts with the steam to produce carbon dioxide and hydrogen. At 700 Kelvin, the equilibrium constant is 5.1. Calculate the equilibrium concentration of all species if 1 mole of each component is mixed in a 1 liter flask. So the difference between the previous question and this one is we have all the concentrations, initial concentrations here. So how can we solve this one? Let's see. Same method, no big difference. Only thing is we have first step always correct, right? It's the same thing. Carbon monoxide combines with the steam. First we have to write the balanced chemical equation, and the products are carbon dioxide gas plus hydrogen gas. So since we have the initial concentration, even though it is given in moles, we know it is given in 1 liter flask. So 1 divided by 1 will be 1 molar, and each one is 1 molar. And now we can see that reactants negative x, because the coefficients are 1 in each case. So this will be plus x for the product. And at equilibrium, we will have 1 minus x, 1 minus x, 1 plus x, and 1 plus x. Okay, and now in that case, now we can write K expression. To write the K expression, what we have to do, products over reactant, and we have the K value given 5.10. So that equal products are carbon dioxide and hydrogen divided by carbon monoxide times water. That's the steam. That is, now I can substitute whatever I have during the equilibrium concentration I have written. So that is 1 plus x, 1 plus x divided by 1 minus x times 1 minus x. So that equal 1 plus x to the power 2 1 minus x to the power 2. So we can take square root on both sides. Square root of 5.10 equal square root of 1 plus x whole to the power 2 divided by 1 minus x to the power 2. So square root of 5.1 is 2.26, and on the right side it will be 1 plus x divided by 1 minus x. And now we can solve for x. So 1 minus x I can multiply on both sides to get rid of 1 minus x from the right side. And on the right side now I have only 1 plus x. And now I will expand on the left side. 2.26 minus 2.26x, that equal 1 plus x on the right side. And then 2.26 I'm rearranging now, minus 1 from the right side changing to minus 1 on the left side, that equal x on the right side plus 2.26, that is negative 2.26 on the left side will change to positive 2.26 on the right side, that equal 1.26 equal 3.26x. So then x will be 1.26 divided by 3.26, that equals 0.387. That's the x value. So we will just substitute in the x at equilibrium. So that means we know each one is 1, coefficient 1 and 1. So the concentration of carbon monoxide equal concentration of water, that equal 1 minus x value we calculated 0.387, that equal 0.613 molar. Same way for carbon dioxide concentration will equal concentration of hydrogen, that equals 1 plus 0.387, that equal 1.387 molar. One more example, you can pause the video, you can try first and then check your answer. So here the question is, assume that the reaction for the formation of gaseous hydrogen fluoride from hydrogen and fluorine has an equilibrium constant of 1.15 times 10 to the power 2 at a certain temperature. In a particular experiment, 3 moles of each component was added to a 1.5 liter flask. Calculate the equilibrium concentration of all species. So what we have to do, first step is we have to write the balanced chemical equation. So hydrogen gas combines with the fluorine gas forming hydrogen fluoride. So when you balance, you can see we have to write 2HF to balance 2 hydrogen and 2 fluorine on the left side. So now we have initial concentration. So they gave us the number of moles, 3 for each component, and the volume is 1.5 liter. So we will have 2 molar hydrogen, 2 molar fluorine, 2 molar HF. And now the change will be minus x plus 2x because of the coefficient. And now equilibrium concentration will be initial concentration minus change, initial concentration minus change, and 2 plus 2x for the products. So now what we will do, we have the K value given. So we will substitute the K value and we will find the X. And now K equal 1.15 times 10 to the power 2. That's the given value. And then we will write the K expression, which is concentration of hydrogen fluoride to the power 2 divided by concentration of hydrogen, concentration of fluorine. That equal, and now we have at equilibrium we have 2 plus 2x to the power 2 for HF and divided by 2 minus x For both it is 2 minus x, so I will just put 2 minus x to the power 2. So now we can substitute and we can find the value of x. So since it is square on the right side, we can take square root of k value 1.15 times 10 to the power 2, that equal square root on the other side will give us 2 plus 2x divided by 2 minus x. So when you take the square root of 1.15 times 10 to the power 2 will give us 10.7, that equal 2 plus 2x divided by 2 minus x. And now we can multiply on both sides by 2 minus x to take off 2 minus x from the bottom denominator from the right side. So that is 10.7. 2 minus x will give us 2 plus 2x. We do not have the denominator now because we cancelled by multiplying on both sides. And now let us expand that. So that means 10.7 times 2 minus 10.7x equal 2 plus 2x. So this one is going to be 21.4 minus 10.7x, that equal 2 plus 2x. And then 21.4 minus 2 equal 10.7x plus 2x. So all the term with x is on the right side now, and that equal 12.7x. And now we can find the x. So 21.4 minus 2 is 19.4, which equal 12.7x. So we will get x equal 19.4 divided by 12.7, that equal 1.527. So we have the x value now. We just have to substitute in the equilibrium concentration. So that means for hydrogen, what we will have is 2 minus 1.527, that equals 0.473, which is same as for fluorine. So I can just write that equal concentration of hydrogen, and which is same as concentration of fluorine at equilibrium. And now for the product side, what we can do is we can substitute the same way. 2 plus 2 times 1.527, that equal 2 plus 2 times 1.527 will be 3.054, that equal 5.054 molar. So we have the equilibrium concentration of all species.